So let's consider another interesting thing here. So we've got an object right here, and I want to change the temperature. So in order to change the temperature, I have to add thermal energy to it. So I have to somehow have energy going into it. Now, it's really hard to define that. So what I'm doing is I'm doing the change in energy. Now you remember change in energy we define to be work when we change mechanical energy. What we do now is we're going to define change of thermal energy to be heat. So work is a change in energy. Heat, change in energy. Heat is not thermal energy, just like work is not thermal energy. Work is the change in mechanical energy. Heat is the change in thermal energy. Well, energy is energy, so you can actually go from one to the other. You can actually change the thermal energy and do work with it. That's the whole point of thermodynamics. That's how engines operate. And so that's that's a basic sort of concept. So if I heat this object here, so I add thermal energy to it, obviously there's going to be a change in temperature. So the question is, well, what's the change in temperature? Well, the change in temperature is going to relate to the amount of heat that goes in, obviously. So the change in temperature has to relate to the amount of heat that goes in. But it also is going to relate to how big the object is. A bigger object requires more heat to get the same change in temperature. Okay, so we write this as the amount of heat is related to the change in temperature. It's also related to the mass of the object, not so much the volume, but the mass. But you also have to include all the other properties, such as the mass of each molecule, the spacing of the molecule, the density of the material, the coupling between the molecules. All this sort of stuff has to be included in there. And so that comes in here as specific heat. Okay, so that little C right there means specific heat. And so this is a property unique to the material. And so each material has its own specific heat. So this gives you an idea that you heat something up and you change the temperature. Well, if you make a graph here of the temperature and the amount of heat that you're putting into it, then this is going to be pretty linear up to a point. At some particular temperature, you keep putting heat into it and you don't change the temperature. What happens is you now are giving so much energy into it that you're actually taking the molecules and pulling them away from each other, so they're no longer as strongly coupled, and now they're able to move around. Now you have changed the phase of it. You've melted it. So the amount of heat it takes to melt something, we call the melting heat, okay, or the heat of fusion, because it works both ways. You can solidify it or you can melt it. So the heat of melting here, okay, is going to be equal to the mass, because the more mass you have, the more that it gets melted, times what we call the latent heat of fusion. That's just something you look up. Now, if you keep adding heat to it, then it starts increasing in temperature again until you reach another temperature. At that temperature, you add more heat to it, and instead of melting, you're actually pulling these molecules so far apart they hardly interact at all. Now you're vaporizing it, you're boiling it. Okay, so this is the boiling point, and this is the melting point. Okay, so the amount of heat it takes to boil something is going to be the mass times the latent heat of vaporization. Again, just something you look up. Okay, so that's again, you add heat to it and you start undergoing a phase change. So these are like the three most common phases of matter that you normally run into: solid, liquid, or gas. We can get more complicated than this. We can talk about what happens at the critical point, where the fluid phases become indistinguishable from each other, or the triple point, because all these temperatures vary as you go from place to place. There's even times in which you go straight from solid to gas. So that'd be sublimation, and in which case you just combine the two latent heats in order to go straight from solid to gas. And so that we can go way more in depth than we have here, but this is just an example to show how all this works. We're out of time for this summer, so we don't really have time to go into all the details. But I did want to introduce some of these ideas. So I'll do an example here of this, and then a couple more examples, and then we'll be kind of done for the summer.